Welcome to Usability and Human Factors, Cognition and Human Performance. This is Lecture C. In this lecture, we continue to consider cognitive constructs that allow us to understand how knowledge is partitioned. In particular, we consider mental models. The lecture also introduces the concept of distributed cognition, an approach that is increasingly important in human-computer interaction and human factors work. After completing this lecture, you should be able to describe the cognitive constructs for mental representation, namely mental models. Explain how cognition and human performance models should inform iterative design processes. Mental models are a construct for describing how individuals form internal models of systems. An individual's mental model provides predictive and explanatory capabilities of the function of a physical system or any kind of system. Mental models can be used to answer questions such as, how does it work? Or what will happen if I take the following action, such as stepping on the brakes while I'm driving? They can also be run in reverse to provide an explanation of what just happened. Why did my system just crash? Or I turned left instead of right and arrived at the wrong place. The running or execution of a model corresponds to a process of mental simulation, which can be used to generate future states of a system. They enable us to reconstruct event sequences which lead up to some outcome or problem. Mental models can also serve as cognitive maps, which serve to represent some spatial arrangement, like the streets in your neighborhood. For example, if you know a city well, you can readily use your mental model to go places you've never been before. Like other forms of mental representation, mental models are always incomplete, imperfect, and subject to the processing limitations of the cognitive system. Mental models play a very important role in understanding users. If you recall Norman's characterization of gulfs, execution and evaluation, gulfs are partially attributable to differences in the designer's models and the user's mental models. The designer's model is the conceptual model of the system, partially based on an estimation of the user population and task requirements. The user's mental models are developed through interacting with similar systems and gaining an understanding of how actions, e.g., clicking on a link, will produce predictable and desired outcomes. Graphical user interfaces that involve direct manipulation of screen objects represent an attempt to reduce the distance between a designer's and a user's model. The distance is more difficult to close in a system of greater complexity that incorporates a wide range of functions, like most medical information technologies. A well-designed system will engage a user's mental models and thus reduce the learning curve. Such a system will build on users' existing knowledge and behave in a consistent and predictable fashion. Let's consider automated teller machines, or ATMs, a technology that we're all familiar with. Most of us have used these machines hundreds of times or more. ATMs have dramatically improved over the years to the point that usability problems are relatively rare. That is also because most users have very robust mental models. Designers' conceptual models have become more closely aligned with user models over years of iterative designs. Users have an intuitive understanding of how, at a functional rather than a physical or hardware level. The interaction with an ATM is limited to a set of functions or tasks, such as cash withdrawal or deposit. The sequence of screens is largely predictable. For example, if you click on withdrawal, a screen will present itself with common withdrawal amounts, as well as a text box that will allow you to key in a particular amount. A test of a mental model is whether we can use an ATM from another bank that may offer a very different screen layout or require a different interaction sequence. For the most part, it isn't all that difficult to make that transfer. It may trip you up from time to time, but we understand the behavior of such systems well enough that we can negotiate any such problems. If we give some thought to the CPOE, or Computerized Provider Order Entry screen that was presented in an earlier lecture, we note that it supports an enormous range of functions. We anticipate that it might be more difficult for users to develop robust mental models. The interactions with such systems are less predictable and present additional challenges for the users. Furthermore, many of the systems support very different models of interaction. It's important to keep in mind that the tasks necessitated by patient care are infinitely more complex than those supported by ATMs. CPOE systems will never be as easy to use as ATMs, nor should they, given the complexity of the domain of medicine. The classical theories of information processing have been incredibly useful in understanding interactive behavior. However, we now recognize that they are limited in understanding how people behave in the real world. The conventional cognitive model situates knowledge and cognition inside the head. Distributed cognition has emerged as an alternative conceptualization of interactive behavior. This framework is partially based on the belief that cognition can be construed as distributed across technologies and artifacts, and distributed socially across different people. Knowledge also resides in the world and is available for us to use. To illustrate the point, imagine an expert use of a word processor who can effortlessly negotiate tasks through a combination of key commands and menu selections. The traditional cognitive analysis might account for this skill by suggesting that the user has formed an image or schemata of the layout structure of each of the 8 menus and retrieves this information from memory each time an action is to be performed. For example, if the goal is to insert a clip art icon, the user would simply recall that this is subsumed under Pictures, which are the 9th item on the Insert menu, and then execute the action, thereby achieving the goal. However, there are some problems with this position. Studies demonstrated that even highly skilled users could not recall the names of menu headers, yet they could routinely make fast and accurate menu selections. The results indicate that many, or even most users, relied on cues in the display to trigger the right menu selections. This suggests that the display can have a central role in controlling interaction in graphical user interfaces. In the distributed approach to HCI research, cognition is viewed as a process of coordinating distributed internal knowledge and external representations, e.g., visual displays and manuals. Distributed cognition has 2 central points of inquiry, one that emphasizes the inherently social and collaborative nature of cognition, including doctors, nurses, and technical support staff in a neonatal care unit jointly contributing to a decision process, and one that characterizes the mediating effects of technology or other artifacts on cognition. We lean on others, including people and machines, to help us think through problems. We can't do it all in our heads. This is a silly example. Let's take a caricature of the classic model of information processing, which places a heavy emphasis on rational processes and the use of memory structures. Imagine that you just entered a room and were looking to find a seat to join an ongoing meeting. You see one and look to sit down. The classical view might suggest that you have a goal and the availability of chairs would satisfy it. You perceive a chair and that evokes a chair schema. You then need to make a determination about whether the object you see in front of you is really a chair and that it is empty and supports seating. The distributed cognition explanation would invoke a more direct explanation between perception and behavior. It is an immediate recognition process that an empty chair affords sitting. No deep thought needs to go into the process. It's almost as if your behavior in this context is entirely reliant on your perceptual and motor systems. There is no reason to give it any thought. You merely act on the basis of a perceived affordance. Does that mean that the traditional model is wrong? Absolutely not. It isn't wrong. It is merely simplified in detail and fails to consider important factors. The human information processing models continue to be very useful in the context of human-computer interaction. Distributed cognition places an emphasis on how external information, such as on displays, post-it notes, etc., shape cognition. The organization of mind is viewed as an emergent property of interactions among internal, i.e., knowledge in the head, and external resources. External resources such as a computer display or a handwritten note are viewed as instrumental to cognitive processes. James Gibson was an influential perceptual psychologist. He coined the term affordances to refer to properties of the world that support behavior. For example, a computer mouse affords a coordinated movement of a cursor or pointer on a display. Door handles, water faucets, elevator panels, post-it notes, menus, buttons, lists, hypertext, and scroll bars are other objects that provide particular kinds of affordances. Structures in the environment invite people to do something. A round door handle invites someone to turn it, whereas a different kind of handle may solicit pushing down or straight ahead. The physical shape of the object affords particular kinds of behavior. Affordance is an important concept in the world of distributed cognition. Distributed cognition emphasizes the process of coordinating internal and external representations. As one becomes a more skilled user, the process of coordinating such representations becomes more effortless. In addition, a more optimal design will strive to find the right balance. A display that offers every single function on the first display is endeavoring to maximize the availability of external resources. The downside is that the display is likely to be so cluttered that finding the right button or link could prove to be difficult. A system such as a database that necessitates that you recall complex query commands has the opposite effect of requiring that you rely entirely on your memory or internal resources. Neither option is optimal. Let's briefly return to the slide of our nurse case manager. Notice how many different external resources that she's trying to coordinate, including 2 computer screens with multiple applications open, paper charts, handwritten lab values on a notepad, and various post-it notes that serve as reminders. Although the environment provides an abundance of external information to guide her remote interactions with a patient, it places an onus on the nurse to engage in complex coordination processes. Perhaps the other end of the continuum would be if the nurse had memorized or internalized all of the information on the patient charts and every other piece of information that she would need to know to structure the interaction with the patient. In the real world, if we had to rely exclusively on our memory, we would be much less efficient and effective. Although it is far from an optimal computing environment, this picture nicely illustrates how cognition can be viewed as distributed across a wide range of external resources. The lectures in this series introduce cognitive theory in relation to a cognitive engineering approach to human-computer interaction and human factors. We considered a classical model of information processing and introduced different ways to understand knowledge. The concept of mental models is particularly important. In recent years, a distributed cognition approach has emerged as an alternative to the classical model of information processing.